A while ago, on March 7th, 2020, I implemented 3D sphere and a torus from scratch. When I implement these algorithms for sphere and a torus, I haven't used normal vector at each vertex point. If I could have been able to compute normal vectors at each vertex of these figures, I could have enabled lighting for my three-dimensional figures. Since I haven't implemented normal vectors when I implemented these algorithms, I could not enable lighting for my 3D scenes. Now, in this episode, we will compute gradient. Gradient enables us to compute normal vectors at each vertex of these figures. If we can compute gradients at each vertex of 3D object, we can also create tangent plane at each point. In this episode, we will learn how to compute gradients over 3D object. Hi everyone, my name is Thomas Kim. Today is May 13th, 2022. This is 112th episode for CUDA SYCL OpenGL MFC tutorial series. This is also 6th episode for numerical analysis. We will implement gradient vector, surface normal, tangent plane. We will use Thomas's Calculus 13th edition, Chapter 14, Section 5, Directional Derivatives and Gradient Vector, Example 6. If you haven't watched my previous video, Episode 111, Numerical Analysis 5, please double-click this link. If you haven't watched my previous video, you may not be able to follow my current and future sessions. In the download source code section, please double-click this link. Show in folder, unzip it, rename 112 gradient. Copy the folder, paste it in your working directory. Start Visual Studio Code, open SYCL, OpenGL, OpenCL, your working folder. Select from folder 112 gradient, double-click partial.cu. Also in the include folder, double-click CUDA extensions. Ctrl V. I will arrange side by side like this. In this file, I will copy and paste these links. Void test gradient. Copy this function name, copy, Ctrl and paste it here. I will disable it. In this file, CUDA extensions.hpp, Ctrl and right before namespace CUDA extensions, template, std, size t, var, index, variable index, type name, func type name, arg, types, auto, fix, arguments, other than, var, idx, func type, forwarding reference, app, std, tuple, arg, types. We have to expand the path const value reference arg arguments using variable type std tuple element t var idx. We pass tuple type. return we capture f, then arguments as reference, variable type b, return type will be variable type. This is lambda or args. We copy from arguments std get var idx args. We set v. V comes from lambda parameter. Then return std apply f args. If you do not know how to use std apply, copy this in the YouTube based IQ 95. Then you can find videos about how to use std apply. std apply plays very important role in modern C++ programming. Now here template std size t var index. I would just copy this part, paste it here. The function name will be partial derivative CPU. Now here we will return derivative 5-point stencil CPU. We call this function by passing f. Then arguments, we need to pass std get var idx arguments. So this function computes partial derivative. Also here int n1 order of derivative. We can also pass n. I will create a few more functions. Template, type name, func type, type name, arg, types, std, tuple, arg, types, gradient, CPU, func type, forwarding reference, f, arg, types, args, context per, std, size tn, size of arg, types. Don't forget 3 dots here. Or arguments std make tuple args using sequence t std make index sequence n. Return gradient CPU f arguments, then sequence t instance. Here we will create one more function. Copy this, paste here std size t ins. Here it will be L value reference std tuple arg types constant L value reference arguments. I will make a carry return here std index sequence. We will pass ins. This is dummy. Sorry, I will make it more generic. Or cut, paste it here. Also here, type name, delta, type, double. I will put a carriage return here. Delta, type, h equals 0.001. Here, h. I will fix like this. Here, return. We are calling this function and we pass int for var index. Then this function takes f, then arguments, then n is default value 1, h. We will expand this parameter pack ins, then semicolon. Here, type name, delta, type, double, delta, type, h, 0.001. Now, let's try it. If it builds successfully, start command prompt, dir nvcc sed c++17 on.exe extended lambda expt relaxed context per partial.cu, hit enter. It built successfully. Now here, auto f, auto x, auto y, auto z. We will try this example first. In Thomas's Calculus, chapter 14, section 5, page 837. We will solve this problem. Copy, paste it here, return x times x times x, x times y times y. This is our function from this example. Now, semicolon here, auto gradient, TCE gradient CPU. We pass function f. We evaluate at point P0, 1, 1, 0. I will copy this, paste it here. So 1.0, 1.0, 0. We are calling this function, and this function calls this function. Print gradient, and there. Now we build again. Scroll up, 930. Sorry, I made a mistake here. I have to provide var index. Now let's build again. CLS n. We have a gradient 2, -2, 1. Let's compare. The result is 2, -2, -1. 2, -2, -1. So our algorithm works correctly. I think this function name is too ugly. Fix arguments, but var idx. I changed the function name and also modify it here. Now, here I will add one more argument. Int n1. I will pass n. We will rebuild CLS n. Now, let's try another example. Page 839. Page 839. Here, we will compute gradient of this problem. Copy. Here, this problem comes from here. Oro G, Oro X, Oro Y, Oro Z. I will copy this, copy, return, paste. X times X, Y times Y. I will make it semicolon, Oro, gradient 2 TCE, gradient CPU, F. The point is 1, 2, 4. 1, 2, 4. Print gradient 2 gradient, and there we rebuild. Sorry, we have to pass G here. Rebuild CLS n. The answer is 2, 4, 1. The correct answer is 2, 4, 1. So our calculation is correct.